Hello class. The notion of work, it refers to the application of force applied over a certain distance. For example, if a constant force of 6 pounds is applied to an object to move the object a total of 5 feet, then we multiply these amounts and say that 30 foot-pounds of work was done. Before we proceed, let's discuss the units that are used in the U.S. customary system and in the metric system. So units of force, in the U.S. customary system, we measure units of force in pounds, whereas in the metric system, we're going to use the unit called a Newton. For distance, we are going to use feet in the U.S. customary system, and in the metric, we will be using meters. And then work, when you calculate work by doing force times distance, in the U.S. customary system, that's going to be pounds times feet, or the unit is called a foot-pound. In the metric unit, it's going to be newtons times meters, so you can call them Newton meters, but there's another word we use for Newton meters. It's called joules. The mass of an object is distinct from its weight. For example, an object weighs one amount on Earth, but the same object, which has the same mass, will weigh less on the moon. So mass is an invariant amount. It doesn't depend on the gravitational pull of the object or the planet or planetoid or whatever that you're on. Same amount of material means the same amount of mass. However, weight is the result of the planet's gravitational pull on that mass. The standard metric unit for mass is a gram, and 1,000 grams is a kilogram. The weight, which is the force exerted by the pull of gravity of an object, is the product of its mass and the acceleration constant due to gravity. So if we're talking about Earth, then an object's weight measured in newtons near the surface of the Earth is calculated by multiplying its mass in kilograms by Earth's gravitational constant, which is the letter G, which is about 9.8 meters per second squared. And when you multiply these units, when you do kilograms times meters per second squared, you wind up getting 1 Newton is 1 kilogram meter per second squared. Let's do a quick example of this. An object has a mass of 1,500 grams. How much does it weigh in newtons near the surface of the Earth? Now I say near the surface of the Earth because technically as you go further away from the Earth's center of mass, your weight diminishes. So that 9.8 figure we mentioned earlier would change if you go further and further away from the Earth. But near the surface of the Earth, we can assume it's relatively constant, which is 9.8 meters per second squared. Anyway, your first objective here is going to be to convert the grams to kilograms. So if an object weighs 1,500 grams, and then we can multiply this by a conversion factor. We know that we want to put grams in the denominator and then kilograms in the numerator so that we can get cancellation of the gram units. And we know that 1 kilogram is the same thing as 1,000 grams. So there's our conversion factor. And in the end, we really just have to divide 1,500 by 1,000, and we get 1.5 kilograms is the mass of that object. Once we know the mass in kilograms, we simply have to multiply the 1.5 kilograms by the Earth's gravitational constant, which we're rounding to 9.8 meters per second squared. And then this calculation will give us 14.7, and the unit here would be newtons. Let's move on to the next slide here, something known as Hooke's law. Now suppose that a spring has a natural length L. The force required to maintain the spring at a length that is x units beyond natural length is given below, where k is some constant. F equals kx. So if you want to stretch this spring a certain distance past its natural length, then it's require a certain amount of force to hold the spring right at that distance. And the more you stretch the spring, the more force required. So that length is L, it's its natural length, but then we go beyond its natural length and distance x. And in order to hold the spring here, it requires some sort of force pulled in this direction. X is not the total length of the spring. The total length of the spring after stretching would be L plus x. For any one spring, this constant k is not going to change. The small positive value of k would mean a weak spring, and a larger value of k would correspond to a stronger spring. So what this means is that every time you stretch the spring an extra little bit, more force is required to go that extra little bit. So if you're trying to calculate how much work is done in stretching a spring, you're actually going to break up the stretching process into little increments, because for each little increment, it's a different amount of force required to move the differential dx. Dx will be the change in x. So our force to move one increment is given really by kx times dx. Kx times dx, this is the work done to stretch one increment. We'll say dx units. When I multiply kx times dx, I get how much work was done just for that increment. And then to get the total amount of work done, work is additive. So if it takes so much work to go the first inch, and then so much work to go the second inch, and then so much work to go the third inch, etc., you just add those works together to get the total work. So this is where the integral comes in. This is doing the sum of all the incremental works to get the total work. If you step back, the general construction of doing a work integral, which we're going to be doing 3 flavors of work integrals, springs, objects of varying weight, and pumping liquid out of tanks, is this integral right here. You need some sort of force component times some sort of distance component. That's F times D, force times distance. And then you do that for an increment, and then you add them up and you get the total work done. So this formula that you're seeing here in the middle is the general formula for just doing work in a variety of cases. But the formula you're seeing right here is the one we're going to use specific to stretching springs, where Hooke's law, or this relationship right here, gets used. Right? In this particular case, the F is the k times x, and then the distance we go that force is the differential dx in this case. Okay, let's go on to the next slide and show you how Hooke's law and this integral for total work gets used. A spring is naturally 20 inches long. A 3-pound weight stretches the spring to 24 inches. Find the work done in stretching the spring from 24 to 30 inches. All right, so a spring is naturally 20 inches long. It's always good to draw a little diagram here. And then I'm going to draw the after image, after it gets stretched a little bit. Okay, so initially it's 20 inches long, and then a 3-pound weight will stretch the spring 4 inches. So we know that. Now, x is how far beyond natural length the string has been stretched. So natural length would correspond to a position of x equals 0. And then if we go to 4 inches beyond natural length, then x is increased from 0 to 4 inches. Now we want to figure out the work done to stretch the spring even further, to go from 24 to 30 inches. Well, given the spring, we have enough information now to determine what the value of k is in our Hooke's law. We know that the force to hold the spring x feet beyond natural length is given by kx. Now, I did just stress we want this to be in feet, because when we're doing a work calculation and you're working in the U.S. customary system, which we currently are because things were given in pounds and inches, then we want everything to be in pounds and feet before I start multiplying them so that I could get a work that is foot-pounds. So back to this spring problem, we want to express both of these lengths in terms of feet. Well, 0 inches is 0 feet. 4 inches is a third of a foot. Okay, so now we can return to Hooke's law right here. So we know 3 pounds is required to hold the spring 1/3 of a foot beyond its natural length. So I'm going to divide both sides by 1/3 of a foot to get k. So k is equal to 3 pounds divided by 1/3 of a foot. And so k winds up getting a funny unit. It's going to wind up being 9, right? 3 divided by a third is 9. And it is pounds per foot. Now, I should also mention that Hooke's law is really a model of the reality for a spring, because a spring can only be stretched so far before it just breaks. This F equals kx is not an entirely accurate model, but it's a good enough model to work with. Once I know k, I'm going to set up the work integral for the spring. So it's kx, that's how much force is required, times the dx, which will be the distance component. Right? This part here is the force component, and we stretch the spring an incremental dx to figure out how much work was done in that increment. Now we just have to say we have to go from x units beyond natural length to x units beyond natural length. So we're stretching from 24 to 30 inches. Then we want to go from how far beyond natural length to how far beyond natural length. Well, natural length was 20, and that always corresponds to x being 0. So we're actually 4 inches beyond natural length to start, and we're going to end at 10 inches beyond natural length. All right, we're trying to figure out how much work is done here. The other thing you want to make sure you do is that the unit limits of integration agree in units. In other words, if we're working with feet and pounds, then you want everything to be in feet. So we have to convert 4 inches to how many feet, right? We already established that that's a third of a foot. If you recall, a double hash mark means inches and a single hash mark means feet. And 10 inches is 10 divided by 12, which is 5/6 of a foot. So those are the limits of integration you want to use. They want to be in feet. We're going to go from a third of a foot up to 5/6 of a foot. Then we put the kx, we discover that k is 9 times x and then times dx. Now mind you, let's keep track of what the units are of these numbers. The 9, it was measured in pounds per foot. We were measuring the x in feet. Well, the differential dx, a change in x, is also a change in feet, so it's also measured in feet. Just think of the arithmetic of units here. When you multiply pounds per foot times feet, you wind up getting pound-feet, which is an appropriate unit for work, foot-pounds. You want the unit of your integrand with differential to wind up being the correct unit for the quantity that you're after. In this case, we're after a work, so we want foot-pounds. All right, this one's a very easy integral to complete. We get 9x squared over 2. And we evaluate from 1/3 to 5/6, and 25/8 minus a half, which is the same thing as 4/8. And so we're going to get a total of 21/8, and this unit will be foot-pounds. Okay, let's go to the next idea. The next idea for calculating work is lifting objects of varying weight. An object with mass 3 kilograms. Now, as soon as you see kilograms, you know you're working with metric units. So you're going to want to make sure all your units correspond to newtons, meters, and kilograms. Now, if they give you conflicting units, like suppose they give you a weight here in pounds, but then a distance in meters, then you're going to have to just make a decision. Convert everything to the metric or convert everything to the US customary units. An object with mass 3 kilograms is lifted 20 meters by retracting a rope that has a mass density of 1/2 kilogram per meter. Find the total work done. Step 1 will be to draw a picture that depicts the scenario partway through the process. Establish that x equals 0 is where the object started. So let's say that this is the 20 meters. So let's say the object is currently right there. So it's already gone up this amount of distance. And we are going to lift the object a total of 20 meters. We're establishing that x equals 0 is where the object started. And we're going to assume that we've lifted it at this point here x meters so far. This problem will ultimately require an integral to solve because of the rope issue. Imagine this object being lifted by retracting the rope. You're holding less and less rope. When you put the rope and the object together and consider how much weight you're holding at any moment, you wind up holding less and less as you lift the object. Now this object right here, let's put a unit on that. We knew its mass, not its weight, but its mass. Its mass is 3 kilograms. Okay, so we've lifted the object x meters, where x will vary. We have to know how much rope we're currently holding, and we're holding 20 minus x meters of rope. Okay, step 2 is going to be find the weight of the system when the object is x meters high. So there's going to be the weight of the object, and there's also going to be the weight of the rope. And also weight is a unit of force. I'm going to use F for force instead of W for weight. The problem with doing W for weight is that we also use W for work, which is a different idea, and I don't want to cause confusion. We're going to do the force of the object first. How many kilograms is that object? Well, we're holding 3 kilograms. However, that's a mass unit, not a weight unit. To convert mass into newtons, we have to multiply it by the 9.8 meters per second squared. That will give us a 29.4, and this is how many newtons. Now we have to figure out, well, what's the force from the rope? Well, how many meters of rope am I holding? I'm holding 20 minus x meters. I have to figure out how much mass of rope I'm holding. This is where the mass density comes into play. This rope has a mass density of 1/2 kilogram per meter. So we're going to multiply this by this 1/2 kilograms per meter. Now if I stop here, look at the arithmetic of units. Meter will cancel meter, and you'll wind up with how many kilograms of rope I'm currently holding. Once you know how many kilograms of rope you're holding, you multiply that by the 9.8 meters per second squared, and you'll get how many newtons. I'm going to multiply the 1/2 and the 9.8 first and get 4.9, and then we have the 20 minus x part, and then the units here are newtons. So the total force, or the total weight of the system, because we're holding object and rope, will just be add these together. So 29.4 newtons plus 4.9 times 20 minus x, and all of this has a unit of newtons. That's how many newtons we're holding if the object is at a position of x meters above where it started. Step 3 will be create the integral that gives the work. So the basic setup of all work integrals is there's a force times a distance. Well, the force is the part that we just wrote. Then we're going to lift the object an incremental amount. The dx is the distance component. This is how much work it is to move one increment. But then we want to add up the work of all the increments to get the total work done to lift the object a total of 20 meters. We're going to start at 0 meters and we're going to finish at 20 meters. The unit of this part of the integrand is newtons, and then the unit of the differential is meters. So these units here need to match the unit of the differential essentially. And you want that differential to be meters, therefore you want your limits of integration to be meters as well. And we get Newton time meter, so that's Newton meters or joules. I'm not going to take the time to do the integration here. I'll leave that to you to do on your own. The emphasis here is just how to set this up, but in the end you should get 1,568 Newton meters or joules. If this problem had been 3 pounds and 20 feet and 1/2 pound per foot, then I would have done everything in terms of foot-pounds. Also, when you're given a weight in pounds, you don't need to multiply by the 9.8. You only have to do the 9.8 when you're given a mass in kilograms that you want to turn to a weight in newtons. Pounds is already a unit of force. When a weight is not changing and it's lifted a certain amount of distance, then you simply do weight times distance. You don't need an integral. The reason we needed an integral here was because the rope was taken into account, and the rope had a constantly changing weight because we were holding less and less rope throughout this process. The next example, a 10-pound monkey. All right, so right there I see that we're working in the US customary system. So there's not going to be any 9.8s that we're going to need to use here. A 10-pound monkey dangles tied to the end of a rope that weighs 2 pounds per foot. Find the work done by the monkey to climb 15 feet up. I'm going to do the same 3 steps that I did in the last example and draw some sort of picture to indicate what's going on here. The rope is tied to the monkey. Why is that significant? If the rope is not tied to the monkey, and the monkey weighs 10 pounds and it simply lifts itself up 15 feet, then we would say 15 times 10 and get 150 foot-pounds. That's how much work is done to lift the monkey. This problem would not be very interesting. However, the rope is tied to the monkey. So by the time the monkey has climbed a total of X feet from the bottom, and we know the monkey is going to climb 15 feet up. So we know this total distance from where the monkey started to where it's going to end will be 15 feet. Notice that because the rope is tied to the waist of the monkey, that as the monkey climbs, the monkey is lifting not only himself or herself, but is also starting to carry more and more rope. This amount of rope right here that I just highlighted in orange is held by the monkey. So we have to actually figure out how much rope the monkey is holding after the monkey has gone X feet. So let's say the monkey has climbed 3 feet, then there should be 1.5 feet of rope underneath the monkey at that point. Right, whatever X is, we cut that in half to figure out how much rope is being held by the monkey. The rest of the rope is being held by the ceiling, so that part doesn't matter. All that matters is how much weight the monkey has and how much rope the monkey is lifting. Okay, so now let's do the force or the weight of the monkey. Well, it was given to us, just 10 pounds. No need to multiply by 9.8. We're already using a unit of weight here. The force of the rope. The monkey's holding X halves feet of rope, and we know that the rope weighs 2 pounds per foot, so we have to multiply this by 2 pounds per foot. So X over 2 times 2 just winds up being X, and look at the arithmetic of units, X pounds of rope. We can do the force of the whole system, or the total force. It's just going to be 10 plus X pounds. So now we can set up an integral. The amount of work done by the monkey is going to be, the monkey will go from 0 feet up to 15 feet, and its force is 10 plus X pounds, and then times the dx differential measured in feet. The unit of the differential always matches the units of the limits of integration. So those are in feet, so dx is measured in feet. It's a quantitatively significant component of our integral. What I just said is super important. The integrand by itself is only pounds. The dx is not just there as a symbolic formality of an integral. It has a quantitative role to play in the situation. It has a unit of measure. It's measured in feet. So when you do the pounds times the feet, and then pounds times feet gives you foot-pounds. It gives you a unit of work, which is what we're after. And you add them all up and you get total work. So we get our total work done. I'm going to again spare you of doing the integration. It winds up being 262.5 foot-pounds. An empty bucket weighs 2 pounds. It contains 1 cubic foot of water. The bucket and water are lifted to a height of 10 feet. but the water was leaking steadily such that only 1/2 cubic foot of water was in the bucket by the time the bucket reached the top. Find the total work done in lifting the leaking bucket. Notice there's no mention here about how we're lifting it, whether a cord is being retracted, and notice there's no information about how heavy the rope is or the cord is that we're using to lift the bucket. This is to suggest that we are ignoring the work done in also lifting the lifting apparatus. In other words, we're ignoring the rope or cord or whatever it is that's lifting this bucket. Maybe a person is lifting it. So I'm going to draw a picture. Let's just pretend we're lifting the bucket by retracting a rope, just for the sake of drawing a picture. So we've got some sort of bucket that's being lifted by a rope. There's some water in this bucket, but that water is leaking. And let's assume that we've lifted that bucket. Remember, you always want to draw a picture of partway through the process. X equals 0 is down here at the bottom. We're saying we've lifted the bucket a total of X feet so far. How much is left to go? Well, we want to do 10 feet total, so we know that this amount is going to be 10 minus X feet. We are ignoring the weight of the cord in this case. That wasn't the case in our first example. Ignore the work for the rope. This question only asks to find the work done in lifting the leaking bucket. How much work is done to lift just that is all we're after. Be mindful, sometimes they want you to take into account the rope and sometimes they don't. Just look carefully in the wording. All right, now to proceed further, we have to figure out how much water was initially in the bucket. Well, it's a cubic foot of water, but I need to convert that to a weight. So I went to Google and I determined that 1 cubic foot of water corresponds approximately to 62.5 pounds. We want to figure out what the force is at this point right here. So what's the weight of the bucket and the water by the time we've gone X feet? Well, because the water is changing weight, because we're losing water, this is where the complication comes in. One way is to make a table of points and to do a linear approach. When the bucket is at the bottom, when X is at 0, then we know that the weight of the water is about 62.5. And by the time the bucket gets to the top, so by the time X grows to 10, we've lost a 1/2 cubic foot, which means that we only have half as much weight. So cut 62.5 in half and we have 31.25. What I'm effectively going to do here is figure out a linear equation between F and X. We know that by the time X is 10, our force is one amount. When X was 0, our force was a different amount. So I'm going to find the linear equation that connects these dots. And why are we assuming a linear relationship? The reason I'm assuming that is because of a phrasing right here. The water was leaking steadily. It's that word right there. So it's leaking at a constant rate. That means that there's a linear change in the weight of the object as the object is lifted. So I want to find this equation right here. Well, if I can find the slope of that line, which I can because I had no 2 points, the slope of this line is going to be change in the F coordinates. So the second F coordinate minus the first one over the change in the X coordinates. And this gives me negative 3.125. And the units were, we had change in force, which is pounds, divided by change in X. Change in X is measured in feet. So this is pounds per foot is the slope. So the equation that I'm after right here, the force equation for the water, is equal to mx. Oh, and look, I know the y-intercept. The vertical intercept is known, corresponds to this point right here. So that's going to be the b if I want to go straight to an mx plus b. So negative 3.125 times x plus b, which is 62.5. This is in pounds per foot. This is in feet, and this is in pounds. But when you multiply pounds per foot times feet, you get pounds. And then add that to more pounds, you get more pounds. So this is our formula that tells us how much weight of water we have as a function of X. And then we have the force of the bucket, but that one's a non-changing weight. It's always just 2 pounds. So the force total, negative 3.125x plus 62.5, and we're going to add to that the weight of the bucket, so we're add 2 to that, times the incremental dx, that's measured in feet, and we're going to integrate from 0 feet to 10 feet. So once again, we have this part of the integral is in pounds, and this part of the integral is in feet, and pounds times feet gives us foot-pounds, and so we have a unit of work done. And then when you finish this problem, the total work done is going to wind up being 488.75 foot-pounds.